So, welcome back. So, in the previous class we discussed about compact embedding from H1 omega into L2 omega. So, this H1 omega L2 omega. So, this injection is compact. So, we not only have continuous embedding, but this embedding is also compact more generally. Okay, so, this is not just the only one, and then we use this one to obtain some equivalent norms on H1 omega, whose usefulness you will see in the second part of this course. So, if we have Hm omega, okay, so obviously this is embedded in J omega. So, you require less number of derivatives. So, this condition. Okay. So, and and suitable assumptions on the smoothness of the boundary, because we are now taking higher order derivatives here, weak derivatives. So, this is also compact. Okay. And you also have, of course, this is more tedious to work, because we do not have the Hilbert space structure here. Okay. So, this again, in fact, you can go for Q here, okay, and for suitable combination of course, you still require less number of derivatives. That is one condition obviously, but then there are conditions on P and Q. So, still you have compact embeddings here. Okay. So, these are all important when we study PDE and when you do the analysis of those PDEs. Okay. So, these are, I mean you can find these compactness results in the books of Keshavan and Gilbert and Tudinger, Bridges. There are so many books. Okay. Today I am going to discuss one such embedding theorem, but not in the Sobolev classes. The question is, so this is basically called Sobolev Lemma in most of the books, or Sobolev embedding theorem. So, this is very important result, especially concerning the solutions of PD. So, we usually pose the problem as a weak problem for a PDE and obtain a solution in some Sobolev class. Okay. Now, the question is, suppose, so this is number of derivatives, that is called order. Okay. Suppose, so initially we may obtain in certain class, but if there is a chance to increase that, so those are called regularity results. Okay. So, PDE solution in some Sobolev class. So, using the tools of functional analysis, okay, and then next regularity. So, in many situations, so it is possible to obtain this M as large as possible. Okay. So, by putting appropriate conditions on the inhomogeneous term or on the initial data or boundary data, okay, as the case may be. So, you will see those things in the actual discussion of PD. Okay. So, now natural question is, if a function belongs to Hm for m large, is it going to be a continuous? Okay. That is the question. So, suppose f belongs to Hm omega, okay, m large. How large, that is we will study in this lemma. Does that imply? So, that is the question. F is continuous or more smooth, so differentiable, etc. So, that is the question. Okay. So, let me begin with one simple case. So, in fact, this is an exercise. Okay. So, this is n equal to 1. Okay. So, a b is a finite interval. What else I want? Okay, I will come back. A b is a finite interval. Okay. So, this is exercise. Suppose u belongs to H1 A B. Okay. So, again recall the definition. This means u is an L2 function defined on this interval, and it has distributional derivative which is also an L2 function. Okay. Then u is actually C half A B. Okay. Okay. So, this means, okay, we all the time we write that, okay, but that what exactly it means is there exists a Hölder continuous function defined on A B with Hölder exponent half, such that u of x equal to u 0 x. Okay. So, that is the actual meaning. So, almost everywhere in A B. Okay. So, this is a nice exercise. Of course, if u is an L2 function, it need not be one continuous, but if you give little regularity even in the equations, namely its distributional derivative is in L2, that makes, okay, the function to be Hölder continuous with exponential half. Okay. So, this is what we are aiming. Okay. So, here for example, this n equal to 1 and this 1, they are related. So, when we finally write the theorem, you will understand that. Okay. So, this n and this 1. So, L2 for example. So, if I put 0 there, so that is H0 is nothing but just L2, no derivatives at all. So, if I take just an L2 function, it need not even be continuous. Okay. For example, Heaviside function. Okay. But if you give little regularity, that even weak derivative in L2 gives us a C half function. Okay. So, one more thing I just want to in the case of R n, there is another way of defining Sobolev space. Okay. So, since you already studied distributions, tempered distributions, so let me just make a remark on that. Sobolev space HSRL. So, now S need not even be a positive integer, non-negative integer. So, S is any real number. Okay. So, for open sets, we are not able to do that because we are counting the number of weak derivatives, but using this definition we can also define Sobolev spaces of fractional order. So, what is the definition here? So, HSRN, let me just write that. So, this is space of all tempered distributions. So, everything is in Rn, okay, S prime. So, we know that if f is a tempered distribution, its Fourier transform can be defined. Okay. So, f cap j, okay, let me give that. So, this S is coming here, okay, and f cap. Okay. So, this f cap as a tempered distribution, but we want it to be a function, and when multiplied by this polynomial factor, we want this to be in L2, of course, Rn. Okay. And let me write, because we are using different norms. So, let me write norm. So, I will put triple norm here, Hs. This is nothing but the L2 norm of this. F cap in L2 Rn. Yeah, that is fine. So, you can verify this is again a, in fact, it is a Hilbert space. So, you use the L2 inner product for these things. So, this is everything is fine. Okay. So, what is the connection between this definition and the earlier definition? So, let me just quickly say that. So, if S is a non-negative integer, so using the properties of the Fourier transform, Fourier transform, so we see that this definition coincides with the earlier one. So, what is the earlier definition? So, we want the function to be in the Sobolev class Hs when S is a non-negative integer. So, f has to be in L2 and its weak derivatives are also in L2. Okay. And that you get from this definition, okay, using Fourier transform properties, Plancherel theorem, etc., and the two norms are equivalent. And the two norms, one norm is this one and the other norm defined in the usual way are equivalent. So, even when you are working in a bounded domain or a domain which is not Rn, if we can extend the function in certain Sobolev class to whole of R n, we can make powerful use of this Fourier transform and then go back. Okay. So, this is one advantage of dealing with Sobolev spaces in the entire space. Okay. See, this tool of Fourier transform will not get when working in a proper domain of R n. Okay. So, with that remark, now I come to this Sobolev lemma. Okay. So, let omega be an open set in R n. So, bounded or unbounded, it does not matter. So, in fact it can be one whole of R n and f in L2 log. Okay. Assume the weak derivatives or the distributional derivatives d I k of f. Okay. So, this means, so I am using, so d k of d x I k f. Okay. So, this is for I equal to 1 to n, these are the coordinates, and so these are the number of derivatives m. Okay. Also belong to L2 log omega. Okay. So, this n is the dimension and m is the number of. So, we are not even using the mixed derivatives. So, I would not even call this h m omega. Okay. So, because I am only using, certainly it is applicable to functions in h m omega, there is no doubt about that, but here the hypotheses are very weak. Okay. Okay. Suppose p is non-negative integer and so here is the condition on this number of derivatives, dimension and this p. So, okay, m is bigger than p plus n by 2. Okay. So, you want enough number of these weak derivatives. Okay. So, this is the condition. Then u belongs to C p of omega. So, these are continuously differentiable up to order p in omega. Okay. Again the meaning of that, let me stress. So, that is there exists u 0 a continuously differentiable function up to order p such that u x equal to u 0 x almost everywhere in omega. Okay. So, that is the meaning we use. So, if an L2 log function possesses weak derivatives which are also in L2 log, sufficient number of time. Okay. So, this m should be larger than this. So, in particular if we take p equal to 0, so m bigger than n by 2, then we get a continuous function. Okay. So, just compare this with the exercise I have stated. Okay. Let me. Okay. So, this all started, this just a remark before coming to this proof. Proof is not really hard, but uses all the tools of distributions and Fourier transform, etc. Okay. So, we will see it is not. So, this all started by Sobolev. So, who this mainly was working on integral representation of functions and such embedding theorems, and then lots of people started working in that. So, in fact, you see this what is integral representation of functions and embedding theorems. Okay, embedding. So, this old Russian school, you see lots of work on this, and Sobolev was the first one to apply this kind of results to PDE. So, in fact, there are I think 2 books. Okay, these are published by AMS. So, and how the tools of functional analysis are used in the analysis of PDE. Okay. So, I will continue the proof in the remaining time, and then maybe I will continue in the next class also. Okay, this proof. Okay, so, it is important. So, this Sobolev lemma, this is proved in several books, but also in different hypotheses. Okay, so, they generally state this as a result in HM or WMP. Okay, WMP, that is also. But here we are not using the mixed derivatives. So, these are all pure derivatives only with respect to that I variable I equal to 1 to n. So, we are not using, for example, del square del xi del xj I different from j. Okay. So, that is interesting. Okay. So, this is in Rudin's book, Rudin functional analysis, okay, Rudin's book. Okay. So, let me start that. Okay. By hypothesis, so let me just write that. By hypothesis, there exists GIK, GIK in L2 log. So, we are just writing the definition of the distributional derivative such that integral omega GIK phi is minus 1 to the k integral f dik phi for all phi in d omega. Okay, I just put some number. Okay, just let it be there. So, this is for I equal to 1 to n, and the number of derivatives k equal to 1 to m. Okay. So, this is just by the definition of the weak derivative. So, let omega be open, small omega, such that omega bar closer. So, I denote it by k, also in omega compact. Okay. And choose so you also see various techniques used in this analysis. So, psi in d omega such that psi is identically 1 on k. So, it has compact support and on k it is 1. So, now define f from R n to R. Okay. So, if you are considering real valued functions, okay, by so f of x is equal to psi x f x if x belongs to omega 0 otherwise. So, if x is okay. So, we are able to define a function on whole of R n. So, we can make use of the Fourier transform, etcetera, etcetera. Okay. So, from local thing we are getting a function on R n. Okay. So, f is in L2 log and psi has compact support. So, that means this f is in L2 of R n. Okay. And since f has compact support and any L2 function is also f has compact support because psi has compact support. So, it is also in L2. Okay. So, verify. So, this f actually in L1 intersection L2 of R n. Okay. So, for a bounded set, this I have said it earlier. So, if E is bounded, we use different this L2E is in L1E. That is boundedness. Okay. Okay. And now, by Leibniz rule, so this big F also has certainly distributional derivatives. So, we can just Leibniz rule we have this. So, let me write that because one shows so d I k of f nothing but so this k let me write r. So, r equal to 0 to k, okay, and this d k minus r psi and dr f di. Okay, then these by definition are just GIR. Okay. So, to begin with, these are distributional derivatives, but since these are L2 log functions and again this has compact support, okay, it's because psi is smooth. So, that implies this again d I k f also belongs to L to R n. So, for all, okay, so let me just not repeat that. Okay. So, now you use Plancherel theorem. By Plancherel theorem, so we make some observations now. The Fourier transform of f and Fourier transform of all also L2 functions. Okay. So, and then you use the properties of the Fourier transform. So, we obtain the following. So, we have this R n over. So, let me use the y variable y for the Fourier transform variable finite, and then you have R n y I to the 2 k f cap y square finite. So, that is essentially the Fourier transform of d I k. So, this is for I equal to 1 to n and k is equal to 1 to m. Okay. And now you recall this easily doable algebra inequality. So, now, so you want to essentially combine this 1 and all these powers into a single power. Okay. So, this 1 plus mod y to the 2 m. Okay. So, I have just put that 2 m is less than or equal to some constant which depends on m and n. Okay. So, anyhow, so this 1 plus y 1 square etcetera y 1 2 m y n 2 m. Okay. Okay. So, this is verified. Okay. So, this is just an algebraic inequality, verify this, and that implies, so we have this integral over R n, this 1 plus mod y to the 2 m f cap y square is finite. So, let me call this. Okay. So, just remember, and you see here itself got an inequality, and compare this with the definition of this Sobolev space in R n. Okay. So, you are also getting something similar here. Okay. So, you can expect them to be very similar, and they are. Okay. I will stop here and continue in the next class from this point onwards. Thank you.